Hello everyone, welcome to the 11th lecture of the course Statistical Thermodynamics. The topic of this lecture is a review of classical thermodynamics, specifically the concepts of Helmholtz and Gibbs energies and the Maxwell relations. In the previous lecture, we have discussed the second law of thermodynamics, which is the central idea of the subject of thermodynamics. If we take a high-level view, there is conceptually nothing more to classical thermodynamics than what we have discussed in the past few weeks. If then you're wondering why thermodynamics books are so thick, the reason is that the material contained in them is about applying the laws of thermodynamics which we have learned to various specific real situations. To do this effectively and in an easy manner, we need to come up with some new definitions and some new secondary concepts, and that is what makes the application of thermodynamics such a vast area of study. With that background, let us consider some specific situations which are particularly relevant to chemistry. Remember that our goal is to calculate the change in entropy of the universe associated with a transformation so that we can understand whether it will occur spontaneously or not. So, we need to calculate the entropy change of the system and its surroundings. Calculating the change in entropy of the surroundings every time a system undergoes a change seems particularly challenging. We will see in this lecture that for some specific situations, it is quite easy to calculate the change in entropy of the universe by only focusing on the system and predefining a few new terms. For the situation when the system is isolated, the change in entropy of the universe is just the change in entropy of the system. So for an isolated system, the criterion for spontaneous change is just delta S system greater than or equal to 0. Let us now consider two more realistic situations in the context of a chemical process or a chemical reaction. The first is a process occurring at a constant volume and constant temperature. The second is a process occurring at a constant pressure and a constant temperature. Let us begin by quantifying the change in entropy of the surroundings for these processes. For any system other than an isolated system, the heat absorbed by the surroundings, Q surroundings, is equal to minus Q of the system. If I don't put a subscript, it implies that I'm referring to the system. The change in entropy of the surroundings for this process is equal to Q of surroundings reversible by T, and this is equal to minus Q by T. For the surroundings, the heat absorbed is negative of the heat released by the system, and it is always reversible because the surrounding has a very large heat capacity and its temperature is always constant and it is always in equilibrium with the system. Now let us consider the first of the two realistic situations I mentioned in the previous slide, and that is a constant volume process. The actual situation you can imagine is a reaction happening in a closed chamber with a fixed volume. Assuming the work to be of only the pressure volume type, if delta V is equal to 0, that is, there is no change in volume, then the work done is 0. Then, from the first law of thermodynamics, du is equal to q. The change in entropy of the surroundings, ds surroundings, from the formula written above is equal to minus du by t. From the second law of thermodynamics, ds of the system plus ds of the surroundings should be greater than or equal to 0 for a spontaneous process. So ds minus du by t from here should be greater than or equal to 0, which implies tds minus du should be greater than or equal to 0, or in other words, du minus tds should be less than or equal to 0. So for the constant volume process, the second law of thermodynamics takes this special form. We will return to this shortly, but for now, let us consider the second type of process, which is quite common in chemistry contexts, which is a constant pressure process. Let us at this point define a new state function in terms of other state functions, which we will call enthalpy, and we denote it as H and define it as U plus PV. Clearly, this state function enthalpy has dimensions of energy. From the first law of thermodynamics, du is equal to Q plus W, and assuming the work to be of only pressure volume type, this is equal to Q minus P dV. So the heat absorbed is equal to du plus P dV, and we can write this heat absorbed in terms of the change in enthalpy of the system at constant pressure. We can see that this looks analogous to Q is equal to change in internal energy at constant volume on the previous slide. So the change in entropy of the surroundings, ds surroundings, is equal to minus Q by T, which is minus dH by T. And from the second law of thermodynamics, ds plus ds surroundings greater than or equal to 0, which implies ds minus dH by T greater than or equal to 0. So TdS minus dH greater than or equal to 0, or dH minus TdS less than or equal to 0. Again, you'll notice an analogy between this equation involving the change in enthalpy and the equation on the previous slide involving the change in internal energy. Let us now introduce two new state functions. Both of these have dimensions of energy. The first one, which is called the Helmholtz free energy and denoted by A, is defined as U minus Ts. And the second state function is called the Gibbs free energy and denoted as G and defined as H minus Ts. We can see that at constant temperature, the change in Helmholtz free energy dA is equal to du minus Tds, and the change in the Gibbs free energy is equal to dH minus Tds. Using these quantities, we can easily define the criteria for spontaneous change for the two situations we just talked about. So going back to the constant volume process that we just discussed, we notice that du minus Tds is just dA. So the criterion for spontaneous change in this constant volume process can be written easily as dA at constant temperature and volume less than or equal to 0. Similarly, for the constant pressure process, dH minus Tds is dG at constant temperature and pressure less than or equal to 0. The criteria for spontaneous change of a system can thus be written in terms of properties of the system itself, and we will now summarize them. For an isolated system, a change will be spontaneous if the change in entropy of the system is greater than or equal to 0. For a system at constant volume and temperature, a process will be spontaneous if the change in the Helmholtz free energy is less than or equal to 0. And for a system at constant pressure and temperature, a process will be spontaneous if the change in its Gibbs free energy is less than or equal to 0. By defining the new quantities Helmholtz free energy and Gibbs free energy, we have made our job of calculating the change in entropy of the universe easy, at least for a certain class of processes. To understand spontaneous change, we can now focus on the properties of only the system rather than keeping track of the system and its surroundings. In the context of chemistry, reactions often happen at constant pressure and temperature, and the condition for spontaneity is that the Gibbs free energy of the process is less than or equal to 0. Note, however, that this is not universally true. The universal statement is still that the entropy of the universe increases for a spontaneous process. So, for a chemical reaction, you cannot generally say that the Gibbs free energy decreases when it happens spontaneously. That is only true under the conditions of constant pressure and constant temperature. Whereas, for any reaction under any condition, the entropy of the universe always increases. That is a completely universal law. We will now move to the second part of this lecture, which is about the Maxwell relations. The motivation for the Maxwell relations comes from the fact that measuring entropy change is experimentally challenging. The Maxwell relations relate the change in entropy with respect to pressure and volume to changes in pressure and volume with respect to temperature, and the latter is relatively easy to measure. And that makes these relations very practically useful. There are four Maxwell relations corresponding to the four state functions: internal energy, enthalpy, Helmholtz free energy, and Gibbs free energy. Let me discuss the procedure for obtaining the Maxwell relations. The first step is to identify thermodynamic relations where the total derivative of these four state functions are written in a simple form, that is, in terms of its natural variables. The second step is to compare this relation with the formal total derivative of the state function to obtain relationships for the partial derivatives. The third step is to use the symmetry of the second derivatives of the state functions in terms of the natural variables to obtain the Maxwell relations. These steps might sound a little complicated now, but they will become absolutely clear to you once we work out the Maxwell relations. After going through that, you can use these steps as a roadmap or a summary to derive the Maxwell relations on your own. Let me begin by deriving the Maxwell relation for the state function corresponding to the internal energy. We start with the first law of thermodynamics. Du is equal to delta Q plus delta W. The heat absorbed and the work done depend on the path, and we will choose a reversible path. So du is equal to delta Q reversible plus delta W reversible for a reversible path. Now we can write delta Q reversible as T ds and del W reversible as minus P dV. So then we have written du in terms of state functions. This equation is applicable to all processes, reversible and irreversible, because this is in terms of the state functions. This equation of internal energy in terms of change in entropy and change in volume is called the fundamental equation. This equation will show up when we write the total derivative of all the other state functions h, a, and g. Since any property of a single component closed macroscopic system depends on only two variables, we can see from here that this is the total derivative of u in terms of the change in variables entropy and volume. So the natural variables of internal energy are entropy and volume. Now let us write the formal total derivative of du in terms of the natural variables, and that is del u by del s at constant volume ds plus del u by del v at constant s dv. Now comparing these two equations, we see that del u by del s at constant volume is temperature and del u by del v at constant entropy is minus of pressure. The final step to derive the Maxwell relation is to use the fact that the second derivative of the state function with respect to the two variables is symmetric. So this is equal to del squared u by del v del s. And if we write this more precisely, this implies that del by del s, del u by del v at constant S, and this is constant volume, is equal to del by del V, del U by del S, constant volume, constant entropy. And now substituting for del U by del V at constant S as minus P, and for del U by del S at constant volume as T, we get minus of del P by del S at constant V is equal to del T by del V at constant S. And this is our first Maxwell relation. We will now derive the Maxwell relation corresponding to enthalpy. We start with the definition of enthalpy. H is equal to U plus PV. Take the total derivative dH is equal to du plus P dV plus V dP. Using the fundamental equation, del U is equal to TdS minus PdV. So substituting that here, dH is equal to TdS minus PdV plus PdV plus VdP. And so dH is equal to TdS plus VdP. We see this total derivative of enthalpy written in the simple form. So the natural variables of enthalpy are S and P. Writing the total derivative formally, dH is equal to del H by del S at constant P ds plus del H by del P at constant S dP, and this implies that del H by del S at constant P is T and del H by del P at constant S is V. Using the symmetry of the second derivative, del H by del S del P is equal to del H by del P del S, which implies more specifically that del by del S del H by del P at constant S and this whole derivative at constant P is equal to del by del P del H by del S at constant P and this derivative at constant S. Now writing del H by del P at constant S as V and this partial derivative as T, we get del V by del S at constant pressure is equal to del T by del P at constant entropy. And this is the second Maxwell relation. Now the Maxwell relation corresponding to the Helmholtz free energy. We start with the definition of A. A is equal to U minus Ts and dA is equal to del U minus Tds minus S dt. Again, using the fundamental equation, du is equal to Tds minus Pdv. So dA is equal to Tds minus Pdv minus TdS minus S dt. Cancelling these, dA is equal to minus PdV minus S dt. So the natural variables of A are V and T. Writing the formal total derivative of A minus del A del T at constant V dt. So del A by del V at constant T is minus of P and minus, and del A by del T should be plus, and del A by del T at constant V is equal to minus of S. Now using the symmetry of the second derivative, del 2A by del V del T is equal to del squared A by del T del V, which implies more explicitly del of del A by del T at constant V, derivative with respect to V at constant T is equal to del A by del V at constant T L by del T at constant V. And using the definitions we just have for del A by del T at constant V, we get del minus of del S by del V at constant T is equal to minus of del P by del T at constant V. And multiplying both sides by plus 1, we get the third Maxwell relation. Now we derive the final Maxwell relation corresponding to the Gibbs free energy. Starting with G is equal to H minus Ts, so dG is equal to dH minus S dt minus Tds. Using the relation for dH, which we obtained while deriving the Maxwell relation corresponding to the enthalpy, dH is equal to Tds plus Vdp. Substituting that, we get Tds plus Vdp minus S dt minus Tds. Cancelling these terms, dg is equal to Vdp minus S dt. And this suggests that P and T are the natural variables of G. Writing the total derivative formally, del dg is equal to del G by del P at constant T dP plus del G by del T at constant P dt, and this implies that del G by del P at constant T is V and del G by del T at constant P is minus of S. Using the symmetry of the second derivatives, del 2G by del P del T is equal to del 2G by del T del P, which implies del G by del T at constant pressure, del P at constant temperature is equal to del by del T by del P at constant temperature, constant pressure, and substituting for del G by del T at constant P as minus S, this becomes minus of del S by del P at constant temperature is equal to del, substituting for del G by del P at constant temperature as V, del V by del T at constant pressure. This is the fourth and final Maxwell relation. The Maxwell relations, as you can see, could be derived very easily using simple math, but the relations are very unexpected. That is, it is completely non-intuitive to imagine that the change in entropy with respect to the pressure can be related to the change in volume with respect to the change in temperature. The third and fourth Maxwell relations are very useful because the variables held constant in them, in equation 4, temperature and pressure, these are more experimentally controllable than entropy and volume, which are held constant in equation 1, or entropy and pressure in equation 2. The third and fourth Maxwell relations can give volume and pressure dependence of entropy from pressure, volume, temperature data, or from an equation of state of the substance. This can be very useful practically. There are several more things we could discuss about classical thermodynamics to apply to specific systems, but in the interest of time, we will stop here. I think we have touched upon all the important conceptual aspects related to classical thermodynamics, and I hope you have got an appreciation for this beautiful subject. From the next lecture, we will take a very different view of thermodynamics. That is, we will begin exploring the statistical picture of thermodynamics. See you for the next lecture.